Good morning and good afternoon and good evening, everyone, and welcome to Building IQ's Ask the Expert webinar. This is the fourth and final one of our first series of Ask the Experts. And today's speaker is Dr. Rami Khushaba, who is one of our senior data scientists at Building IQ. Before we get going, my name is Steve Nguyen. I'm in the marketing and product departments here at Building IQ, and I'm your host. So with that, I'd like to introduce today's speaker. Dr. Rami Khushaba is a senior data scientist with Building IQ. He has more than 10 years experience in developing various signal processing and machine learning algorithms for a variety of different projects in human-computer interaction. These include the control of prosthetic devices for amputees, driver drowsiness and distraction detection, cognitive neuroscience, and many more. Rami is an accomplished speaker at technical conferences and is extensively published, and in fact holds 3 patents as well. Dr. Khushaba is our main contributor to our upcoming causal relationships engine and data-based fault detection modules. Rami holds a PhD on human biosignals processing and machine learning from the University of Technology in Sydney. He also has a master's degree in electrical engineering and a bachelor's degree in computer and control engineering. And with that, I would like to now hand it over to Rami.
Thanks, Steve. Good morning and good afternoon, everyone. As Steve mentioned, I'm a senior data scientist with Building IQ. I've been working here for the last almost year and a half, and today I'll be talking about our living and breathing buildings. So first of all, I will talk about how could someone with a background in biomedical signal processing jump into this field. I would like to start by showing you one nice slide here. As you can see, I'm comparing actually the human beings to commercial buildings. So basically what we do as human beings, we breathe air, while commercial buildings, they breathe energy. So if you look at these screen captures that were provided to us with the kind permission from ResMed, you can see that the flow signal, which is the signal that you usually get from your nasal cannula, the other signals are thorax and abdomen. If you look at the flow signal in the left screen capture, it shows you that it almost looks like a sinusoidal signal over here in this example. And if you look at the bottom screen capture, which is coming from our portal, you see that the total building power also looks like the sinusoidal signal in like normal days, let's say around the 23rd of February around this area. In terms of your breathing can be disrupted by certain conditions. So if you look on the right screen capture over here, you can see that there are certain patterns that appear on your flow signal or your breathing, including the flow limitation, which has an early like spike in the beginning of the breath and then flattening in the breath. And we also have something similar over here on the total building power, when your power overshoots when you start on early morning on Monday. And for those working in this field, you probably have seen something like this, where the HVAC is usually off and it kicks in. There's a fixed set point and it needs to bring the temperature down, and the HVAC will be operating in a heavy way to make that set point drop down, or make the zone temperature drop down to the set point level, and this is why the energy spikes. Also, on your breathing, you could have an apnea, which is a problem because it's basically the cessation of breathing, which is like you stop breathing. You could have also something similar on your total building power. But if that happens over here, like during the weekend, that is not a problem at all. But if it happens during a working day, then that's a problem. Why did the building stop breathing energy? So this is like a nice similarity between the two. But what we have an advantage for in terms of commercial buildings is that the falling cost and increased accessibility and the IoT devices have nowadays like allowed us to have access to every single measurement from all the sensors within the building. But the missing part is the intelligence. So we have access to all of that data, we can make use of it. And we need to see first what are the problems that we usually encounter with commercial buildings and how we tackle these from a data science perspective. So let's jump into the commercial buildings problems and let's have a look into what's going on over there. In terms of commercial buildings, as you may know, the large-scale commercial buildings account for almost 30 to 40% of the total energy consumed worldwide. And the heating, ventilation, and air conditioning systems, what we call the HVAC for short, HVAC systems in these buildings, they account for almost 50% of each building total power consumption. And these HVAC systems, they are known to operate in an inefficient way, which usually results in huge energy and dollar waste. So looking at the status quo, what's there in the industry before building IQ, temperature control is usually static. Scheduling is done independently for each zone or room with no global coordination. Another problem is that it's usually the operation is agnostic to dollar cost of energy, the time of use tariffs, leading to huge waste in energy and dollars. And usually there's no use of the underlying building physics. Of course, if you understand the physics and incorporate them in your operation, that will add a huge value.
Hey, Rami.
Yes.
A question came in. Human bodies are pretty much the same, but commercial buildings, at least my commercial building, is different from most everything else. How is it that you can apply the data science to my building? Because it seems like all of your previous work is around the human body.
Well, that's a really good question, Steve, because we say that every single one of us is unique, right? But the physiology that drives how our bodies operate, it's the same. Look at the blood circulation and these kind of stuff happening. So the underlying mechanisms that control the behavior or the operation of our bodies, there's something similar in the buildings field. Every single building is unique, but the operation, or let's say the underlying principles, are the same. So there is no much difference. So you can still apply the same methods that you have in the biomedical signal processing. You can still bring them here and adapt them to serve these buildings.
Thanks.
Okay, you're welcome. So moving forward, how do we solve these problems from a data science perspective? What we do, or what we say usually, we have big data methodologies applied to big buildings to give big savings on big energy bills. Everything is big over here, as you can see. So how we approach the problem at Building IQ, we have three set of tools, including basically the analytics, measurement and verification, and energy and operation optimization. So in terms of analytics, we have a huge set of analytics, including descriptive, those that tells you what happened in the past, diagnostic analytics that tells you why did a certain thing happen, predictive analytics that will tell you what will happen in the future, and perspective analytics, which will tell you what should have happened. In terms of measurement and verification, this is a really important part that we focus on since a long time, which is basically a method to baseline the performance of your building before we jump in. So we need to know how your building behaved in terms of energy consumption, and then we based our savings estimations on this one, measurement and verification. Over here, we have a huge library with so many machine learning algorithms, including support vector machines, neural networks, random forest, regression models like lasso ridge and elastic nets, and so many others. In terms of energy and operation optimization, we started with the predictive energy optimization models that we collaborated on with CSIRO. So the first original models came from CSIRO, but then during the last years, we have been actually extensively revising and further developing these models. And like recently, we also added reinforcement learning version to predictive energy optimization, and it's nowadays active on few buildings already testing that.
Question, Rami. On M&V, the question is, how is your M&V different from M&V 2.0, or is it the same?
Well, our MNV is like kind of unique, and I will go into that right now in this slide. Measurement and verification is kind of like the 5 pillars that Building IQ offers. So 5 pillars of the Building IQ 5i platform. So the way we do it, we have two approaches. We have one approach which is based on historical data that looks at the historical metadata and weather data and some other features that we have developed in-house, and use these to create a performance baseline. And the other approach is a kind of a periodic on-off test where you get 1 to 2 weeks of usage data collected, then you turn off Building IQ optimization, then another 1 or 2 weeks of building data collected, and then you turn it on, and then you keep cycling in that way. So what's unique about us is that our methods are highly verified. They use the latest machine learning algorithms with the latest feature engineering tools. So we have some thermal models that we use in our MNV models, and we include so many features, including outside temperature, humidity, time of the week of the year, of the month as well, and so many other parameters. But the nice thing about this is basically a measurement of the causal impact. So let me show you this example over here where the x-axis is time and y-axis is the energy. So the dotted line over there, the vertical line, is where Building IQ came in to start control this building. The blue curve is the measured actual energy before us. So this is what we baseline. So we create some models, like regression models, to model the behavior of this curve. And then after we hooked up our optimization technology to this building, the red line over here is what the power should have been look like. But because we started to control this and we implemented our control strategies, you can see that the actual measured energy is much lower than that. And the difference between the two curves, when you consider that with the time of the use tariff, is the amount of energy we have saved you. And we will tell you exactly in dollars how much we saved you during this period. And I'll show you one example over here. This is a real commercial link from our portal for 1 week in July, the 15th of July. And you can see around the first 3 days, which is Monday, Tuesday, Wednesday, the purple line tells you what the actual power should have been, but the red one tells you what the actual power is right now. The difference between the two is the amount that we have saved you. However, on the fourth day of the week, which is Thursday, you can see that the power spiked over there. And usually, although that we have saved some energy over there, but then usually the question comes in, why do I have a spike over there? And this is where we use our analytics and our upcoming smart engine to figure out the root cause of this spike. Why did it happen? What caused it to happen? And every single other point involved in this problem, if there is any problem. As I said, this is a way to measure the performance before and after Building IQ. So what Building IQ does, as I said, is adding the control strategies. So let's talk about the control of smart buildings. Usually the normal control methods, it's all about setting the temperature set points, or one of the approaches actually is about setting a fixed temperature set point, which is the green line that you can see over here, and a fixed comfort bounds. So when the HVAC is off and then it kicks in when there's like the building operation starts around 8 a.m., as you can see here in the top graph, there is a huge operation or huge like involvement from the HVAC to get that room temperature down to the required set point. And this is where the energy spikes, as I showed in the first example in the first slide. So how we do it differently in terms of Building IQ, we have actually allowed the comfort bands, as you can see here, to be changing through the day. And we also change the temperature set points dynamically also through the day. So the whole operation over here is like kind of complicated. And those guys, like the building operators, they do a really good job in managing these huge mechanical systems. I show you here one example from it. There are so many parameters involved in the control of this system, like supply air temperatures, supply air pressures, fan speed, the eco cooling, the PID loops, and so many other things. So what happens, for example, in this AHU is that you get the air, like outside air, you get it inside the AHU system, it goes through some filters and then pass through the heat wheel over here, which kind of operate at a fixed speed to combine the returned air from the ducted systems with the outside air and push it through the filters. And then if you need some further cooling, you lower down the temperature and send it through extra filters and then through the supply air ducts to the zone. So the operation is not easy, but what we have is a smart control strategy that looks at so many variables. So we look at the cost of the energy, the weather forecast, and so many other parameters, as I will show you in a second. So in that example, again, referring back to this example over here, if you start at time 0, what we say, we have a forecast, which is the blue. We have a forecast of the outside air temperature, how it should look like. And then what we do over here in this example, we cool down the building when the energy price is low. And during the time when the building operation starts, we let it drift. But then, as you know, weather forecasts change. So if we find a change, what we do is that send a updated profile. And the comfort bands will also be changing if allowed by the ops, of course. This is how we like have more freedom into the control of the buildings. So we send these profiles. And what we do like basically is our optimizer send the zone target temperature profiles to the site agent. And if the ops allow us to control the VAVs, we'll be sending these to the VAVs. But if not, then we have a smart control agent that will actually send these to the supply air temperatures and supply air pressure or duct static pressure, and will also affect the fan speeds as well, as you know. Another control strategy that we have is the predicted mean vote. which I'm pretty sure that most of you are actually familiar with. So it looks at metabolic rates and many other physical parameters. And it also sends these target temperatures to the site agent, which will either send it to the VAV or the SAT side and duct static pressure side again. Additionally, we have also a recent approach, which is a cause-based heuristic optimization approach, which goes straight away to the supply air temperatures and looking for the power profile that costs less. And this is one of the recent additions. So speaking about our optimization engine, when we said understanding of the physical parameters of the building is really important, because what we do over here is that we have built this model based on physics. And then this model needs to be adapted to your building because, as you said, your building is unique and we understand that. So what we do, we bring our physical model, we optimize the parameters of our model based on your own building data. So we have incorporated information from your data, like we have adopted this model specifically for your building to serve your purpose or to serve your own building and the way it operates. Once we have got the training part done and we have estimated the parameters, we'll be sending the zone target temperature as I explained, and then we will be updating these every 4 hours for you. But internally, you need to know that we actually do this every 2 minutes in our own engines. So think about this in a similar way, like if I'm using, for example, let's say Navigator or Google Maps, when you go from point A to point B. For example, Google Maps will tell you, okay, this is the best path for you to follow today. But while you are driving, Google Maps does some sort of calculation. And if there's some sort of extra traffic or heavy traffic somewhere, it will tell you like, hey, I think there's a problem in this road. I will change you to another road. So this is something similar to what we do with building energy and the profiles that we send to the buildings. And the good thing over here is that in large buildings, a temperature movement by like 0.5 Celsius can save you a massive amount of energy. And this is the part about our building optimization. However, most of this actually existed some time ago, and all of us in the data science team at Building IQ have been adding different models to each of the MNV building optimization models and to the analytics. However, the new part that I'm more excited to tell you about today is our upcoming outcome-based fault detection engine. So we have a huge set of heat maps nowadays that we have very recently developed. These heat maps looks at the performance of all the points, all the map points from your building, from all the zones, and monitor the performance of these. So in one example, we look at the impact of these map points on the total building power or on the sub-meter power. And we monitor this on a longitudinal basis. So we'll monitor this across different periods and time. And then if we see a certain component in your building has suddenly started to cause more energy usage or leakage, then we say, okay, why is it suddenly like using way more power than it has been using historically? So we start tracking that with our different heat maps and with our causal relationship engine. So what we do over here, we go through all of the points, we estimate the causal impact of each of the map points on the different points, and we graph the causal relationships, as you can see here in a small example. And the good thing about this is that you can add extra layers of information or filters that can further refine these graphs, because honestly, we have seen buildings with thousands of points, and if you have a look at the resulting graph, sometimes you can't even read it because there are so many map points. So what we do for you is that we filter these based on the problems and issues and faults that we find, and we look at the relationship between these points. So if I find a fault in one of the points, I start tracking it. I say, okay, who's this point connected to? Who does it impact? What other points does it impact? Who impacted? What other points impacted this point? Where is the fault coming from, and how is it propagating to the different points? So over here is one example where we were tracking some sort of oscillations in one of the buildings here in Sydney. And I'll show you some actually graphs about the point relationship and how we track a problem in one of the examples. So we were looking at the oscillations as one example, and this is the part where I talked about your snoring. So think about the building kind of snoring. The oscillations in the building, as you can see here, it was like showing mutual oscillation, or the chiller enable was oscillating at the same exact frequency with the zone temperatures from 3 different zones. And I also had a look at another example where the boiler return temperature and boiler supply temperature were all oscillating with the boiler status at the same exact frequency. So I said, okay, but who impacted who? Did the boiler return temperature and supply temperature affect the boiler status, or was it actually the boiler status impacting these? What happened? So for someone like me coming from a different field, I wouldn't know much about the mechanics as the ops do. But what I can do is that I can look at the data to tell you what is actually happening. Where is this kind of behavior coming from? So we used our causal relationship engine, and we had a look at this specific example. What we found is like the boiler return temperature and the boiler supply temperature were both impacted by the boiler status. So boiler status, the changes in the boiler statics, the oscillation over there, were actually causing the boiler return temperature and the supply temperature both to oscillate. And then when we looked at the points that by themselves affect the boiler status, we found that the hot water valve over there in this example was actually oscillating. It was the one that caused the boiler status to oscillate, and boiler status by itself started impacting the other points and caused them to oscillate as well. I
Rami?
just want to tell, yes.
Question came in about oscillations. Does that mean that you can only find relationships when they're doing the same thing? Because you're talking about oscillations and everything is oscillating. So my interpretation of that question is, what if it's not oscillating, but it is still impacted by the oscillation? Would your system pick it up?
This is another excellent question, Steve. Our engine can pick up all kind of faults, not necessarily oscillation. We can pick up flatlines, spikes, major activity change, pattern change in general, oscillation. Like we can pick up so many things. I just gave you the oscillation example because it relates to the snoring example that I put in the first slide. So I wanted to make it more intuitive for those who don't come from building ops like background, from like mechanical background, someone like from my side, for example, from biomedical engineering perspective. So I wanted to make it easier, but we can pick up any change basically. And we have new models. I don't want to talk much about it because still until like patents kind of thingy. So our models use information theory and so many complicated like probability-based methods. So I don't want to talk about it much. I'm not allowed to talk much about that side, but don't worry, we can pick up most of the issues that you can ever encounter in a building.
Yeah, I think that wasn't quite the question. I think the question is, let's say, Mike, when I read it, is like you found an oscillation point. The question then is, what if the other points that are moving another point that is impacted is not oscillating but has a pattern change, but it's not an oscillation? Would what you're working on pick those two up as being related or causal? Because one's an oscillation, one is not.
If there is information transferring from the original point to the point that is oscillating, we will pick it up.
Okay, that was the question, I think.
We will pick up any causal impact, regardless of it oscillates or it doesn't oscillate. So if point A is not oscillating, but it has certain impact on point B, which is also oscillating, yes, we will pick it up, regardless if the point B is actually also oscillating or not. Any kind of causal impact will be picked up in this example. But what we are saying, we have extra filters to pick up also the points that are causing each other to oscillate, or those other oscillating at the same frequency and not necessarily causing each other as well. Some like curves can be actually highly correlated, but correlation does not imply causation. That's really important point. So speaking about this, we found the problem. It was a small building with one hot water valve, and PID loop tuning was required for this case to solve the problem. We have also worked with so many much bigger examples with so many hot water valves and many other sensors from different zones. We can pinpoint the exact problem in which zone and identify that straight away to you. And nowadays we also have like apps to do PID loop tuning, and this is done by my colleague Ray. But the correlation engine is the part that I contribute over here. So one last thing, which is really important to keep in mind, is that artificial intelligence is doing a great job in helping us pick up all the kind of faults and automate that and give us a list of top 10 or top 20 problems. But you still need people. The human expertise is still required because cost, region of interest, and available funds must be taken into perspective. So imagine that you find top 10 faults. And you know that one of the faults relates to one of the zones, and this zone is going to be used tomorrow. There's a function in that specific zone. So you can prioritize that. So for reasons like these, and from budget perspective, we say that a combination of AI from a building paired with a National Operations Center, the NOC, to filter qualitative needs of clients is the best strategy for resource-constrained facilities.
Last question came in. Does Building IQ interface with all types of building automation systems? I can answer that one, and the answer is yes. It's a somewhat qualified yes, but a yes. We work with any building system that can output through a BACnet IP interface. or structure-aware interface, and we have some drivers as well. But generally speaking, if your system can be output through BACnet IP, we're good to go, which means that we could potentially put a Niagara front end on it and access the BACnet data through the Niagara front end from Tritium. So with that, if there are any other questions, you can mail them to myself or to Rami directly. Thank you, Rami. Thank you, everyone, for attending.
Thank you very much.
Thank you very much.
Thanks, Steve. Laura, thanks, everyone.
Thank you. Bye.